today's computer. Good. So now, my voice should be being recorded. The screen is being recorded. Everything works. Okay. So now let's start today's lecture. Okay. So before we go over the breakfast search and before we go over the tree search algorithm, I've actually found a video on the X application, okay, on the X app, okay, created by this person now, okay, okay, uh, that is able to illustrate, okay, tree search algorithm, okay. So we'll start today's lecture by taking a look on this video, okay? So essentially this video is actually showing how the tree search algorithm is able to solve a maze, okay? In Chinese, that is called 迷宫, okay? So essentially in a problem of maze or called 迷宫, okay? You essentially have a starting point, okay? You essentially have a starting point, okay? And you essentially have the endpoint, okay? Okay. Maybe I will try to okay. Okay. So the problem, okay, is to find a route, okay, to such that the agent can go from the starting point to the ending point, okay? So this is called a maze problem, or that is called 迷宫, okay? So this is the core idea of the problem. Okay, you have the starting point. Okay, and you have the ending point. Okay, and the white lines here are the routes that the agent can travel to. Okay, and the black lines essentially is indicating the walls that the agent cannot walk past. Okay, and essentially we want to find a path along the white lines, okay, that connect the starting point, that is the top right, the top left hand corner, to the end point, that is the bottom right corner. Okay, so this is the definition of the maze problem. Okay, okay, okay. So any questions? Any questions? Any questions? Any questions? And essentially, what we are going to do is to find a route from the starting point to the end point. Okay? And now in the screen here, you see there are two mazes at the left-hand side and the right-hand side. These two mazes are the same exact maze, okay? But these two mazes are solved, but the left-hand side and the right-hand side are showing two different tree search algorithm in solving the problem. The left-hand side is so-called the best first search, and the right-hand side are so-called the depth first search. Okay, these two search algorithms are different because they are using different search strategy to prioritize nodes being selected for searching. Okay, okay, okay. If you refer back to no. I don't need this. If you refer back to lecture 3, okay, we actually, when we talk about tree search algorithm, we essentially illustrated the concept of tree search algorithm is that we simply keep on picking nodes that has not been explored, okay, and we keep on exploring, okay, and the idea of this algorithm is that we will need to first of all have a search tree that keep track on the path that we have explored so far, okay? And we also need to have a data structure that keep track of what node we haven't done exploration so far, okay? We in the previous lecture we actually talked about the tree search algorithm is that we start out from the initial state and we explore the neighbor state, okay? And for the neighbor state of the initial state, we also explore its neighbor state, okay? We don't care about we keep on generating, okay, the path that starts from the initial state, okay? As long as we have a path that reaches the goal state, then we call our algorithm as finished. Okay? Okay, so this is the main concept you should remember. Computer is not like humans, okay? Unless we teach computers how to intelligently select the path, okay? At the end of the day, it is just trying to generate all the possible pathways and hoping one of them reaches the goal state. Okay, so this is one thing you must remember. Okay, you may think that this is against your own logic, okay, in solving problems like this, okay, because human will just will ignore part of the graph, okay, by using iteration. But yeah, unless you program the iteration into the computer doesn't have iteration. So what it does is just try to generate all the possible pathways, and if one pathway hit the goal state, then it's called the end. Okay? Okay? So up to this part, any questions? So up to this part, any questions? Any questions? So when you are keeping generating path, then you will need to have a data structure to keep track on the path you generate, okay? And we don't just want to have a bunch of linked lists in our memory. So we join them together and form a search tree. Okay? Okay. So essentially you can consider the search tree as a clever data structure that keep track all the pathways. Okay, it is substantially a different usage than the binary tree you learn in data structure. Okay, okay, but it is how it is. Okay, okay. We want, instead of storing all these pathways into a bunch of linked lists in our main memory, we gather them together and we use the ordering of the nodes in the path, okay, as the ordering of the nodes in the tree, okay, so we can have depth in the tree. Okay, okay, okay. So the first element, okay, the first element in the search tree, that is the initial state, is the root, okay, and the second node in the path, okay, the second node in the path is the second layer of the tree, and so on. Okay, okay. You can consider the search tree in our algorithm as a collection of linked lists. Okay, okay. So it is substantially different from the binary tree you have learned. Okay, and to understand the concept of search tree, you need to have the mindset that in this world, binary tree is not the only kind of tree. There are many different kinds of trees for different algorithms. Okay? Okay? So any question up to here? Okay? And we will also use a data structure to keep track on all the nodes we haven't explored so far. Okay? So for example, we start off with initial state and we have 3 neighboring states that we can explore. So now when we discover these 3 neighboring states, the initial state is now being explored. Okay, and now the 3 neighboring states are available for exploration. Okay, so if you take the search tree as if you use the search tree to help you with your understanding, you can also consider all the unexplored nodes are essentially the leaf node in the search tree. Okay, and we are using a data structure to keep track on what node that should be explored first. Okay, and choosing different strategy would affect what node is being explored. Okay, if we choose the shadow nodes, okay, then it becomes the preferred search. If we choose the deeper nodes, then we call it as the depth search. Okay. When consider search tree like this, okay, you have nodes that is being added to the search tree earlier, and they are in a shadow position in the search tree. And you also have nodes that is added later in the search tree. They are in a deeper position in the search tree. So our issue is we should prioritize what node first. Whether we should prioritize the shadow node first, or we should prioritize the deeper node first. And this is our question. Okay. And the depth search is prioritizing deeper node first, and the breadth search is actually prioritizing shadow node first. Okay. And now let's check out the differences between the breadth search and the depth search. Okay. So in this video, okay, so we are trying to, and this video is made by a personnel called a personnel called this. Okay, I don't want to pronounce his name because I don't want to do injustice in calling his name. It should be Dan something. Okay, I don't know how this name supposed to be pronounced. Okay, it's made by Dan. Okay, a person who is releasing e-books on the internet. Okay, and I've actually discovered this video, and this video is comparing the how essentially breadth search and depth search is being executed. Okay, and the essentially is trying to illustrate the differences of these two algorithms using the maze problem. Okay, and essentially in the maze problem, all the white lines here are the path that the agent can travel through, and the black lines are actually the walls, okay, that the agent cannot go through. Okay, and you need to find a path from the top right corner to the bottom left corner. Okay, and this is the left hand side and the right hand side are showing the how the breadth search and the depth search will solve the maze problem. Okay, so let's play this video to see essentially how these two algorithm performs. And as you can see here, when the breadth search is being performed, it is covering the maze. It is covering the maze in a tile manner. Okay, it gradually, you can even see a search fun line. Okay, spreading through the whole search tree, spreading through the whole maze. Okay, so this actually shows the properties of the breadth search. Okay, because breadth search is choosing shadow nodes over deeper nodes. So essentially, it is searching the search space in a layer by layer manner. Okay. I finished the first layer of the search tree node first, and then I start the second layer search. I start the second layer node search on the search tree. Okay, and I start the third layer and so on. Okay, because the fact that breadth search is searching the search space in a layer by layer fashion in the search tree, so you can see that where it is searching the maze problem, the red line is indicating the path that already searched by the breadth search, and the white line is and the blue line is showing the line that have been covered by the depth search. Okay, so you can see at the left hand side, the breadth search is covering the maze in a layer by layer manner, starting from the top left hand corner. Okay.
Sorry, can you?
Yeah. So you can see it is gradually covering the maze from the top left hand corner in a gradual layer by layer manner. Okay, in a gradual, just like having a tile go, just like having a wave starting from the top left hand corner, pushing to the bottom right corner. Okay, just like having a wave. Okay, is the reason why is that the breadth search prefers shadow nodes. Okay, so essentially how the breadth search will execute is that it will actually go through one layer of the search tree and then go through the second layer of the search tree and then go through the third layer of the search tree and so on. Okay? Okay? And you can also see that when when you observe the breadth-first search, you can also see that the algorithm is being executed without any iteration. It's just try out all the possible pathway that you can have in the maze, and at the end, you can find the path. Okay? Okay? So this also explain the core idea of the tree search algorithm. It's just try best to generate all the possible pathways that the agent can go through. And when there is one pathway that reaches the goal state, that it ends. Okay? Okay? I understand that this is unintuitive and un-AI for every one of you. You will find that I have an algorithm. That means that my algorithm should inherently choose a pathway that reaches the goal state without exhaustively checking all the possible solutions. But in fact, this is how breadth-first search really works. It just explore all the possible scenarios. Okay? Both the breadth-first search and the breadth-first search will try its best to exhaustively check all the possible pathways. Okay? Until a valid solution is being found. Okay? Okay? So if you take a look on the breadth-first search side, you can actually see when at the end of the search, there are some sections of the maze that have not been covered with the red color. Okay? Okay? The reason why is that once the solution is being found, then it will stop exploring. Okay? And for the situation on the breadth-first search, when it reaches the goal state, almost all the area of the maze have been covered, but some two sections of the maze have not been searched, have not been explored. Okay, so that is why you will see in the breadth-first search, almost all the regions of the maze have been explored by the algorithm, but part of it have not been explored. The part of the maze that have not been explored, they have not been explored is because the agent already find a path, so it doesn't need to explore the remaining region. Okay? Okay. So any questions? Any questions? Using this graph, do you think that is easy to understand? Okay. So this is essentially how the search algorithm really works. Okay. The main principle of the algorithm is that I don't care. I keep on generating path, and if once I reaches the solution, then I stop. So that is why you can see a little region of the base haven't been explored by the breadth-first search. Okay. Okay. So any questions? Any questions? And for the depth-first search, okay, if you take a look on the depth-first search, that is on the right-hand side. When the depth-first search keep on executing, okay, it is actually not doing it in a wave manner. Okay, in the breadth-first search, you can see that the search is done in a wave from the top left-hand corner to the bottom right corner. Okay, to the bottom right corner. Okay, but in the depth-first search, okay, essentially you can see in the diagram that it will actually go through one path as far as possible, and when that path doesn't reach the goal state, then it will try another route. Okay, so you can see here in the depth-first search, okay, the blue line is indicating the path that the agent explored so far, and let's notice this part, okay? Let's notice this part, okay? The agent is going through this route to see if this route is able to reach the goal state, okay? So it keeps on searching and it finds that this route, okay, going through this route and at this point going up, okay, doesn't lead to the path to the goal state. So it will try an alternative path. So as you can see here, it will try to go at the bottom route, okay? Okay. So at first, so for the depth first search, you can see that it generates a path reaches here, okay? It doesn't search other path right here, okay? It stick to one path and reaches this point, okay? And when it reaches this point, it have more than one choice, so it choose to go up first, okay? It chose to go up to see if it reaches the goal state, okay? But clearly, if you go up, you can see no route going to the goal state. So what it will do is it will try another route to at the bottom, okay? So you can see the properties of the depth first search is vastly different from the breadth first search. The depth first search will not explore all the path in a way, okay? It will stick to one direction, one path, and until that path doesn't lead to the goal state, then it will not stop. Okay? Okay? You may find that, Professor, why the algorithm will go up? There is no way that the going up will lead to the goal state. The idea is the same as the breadth first search. The algorithm internally, okay, is just exhaustively checking all the possible routes. Okay? The algorithm essentially is just exhaustively going through all the routes. Okay? Okay? So because it is doing it in an exhaustive manner, it doesn't actually care whether the path can lead to the goal state. The idea of the breadth first search is that where it will go explore one route and go to explore it as deep as possible. Once that path doesn't reach the goal state, okay, doesn't lead to the goal state, then it will stop and try another route. Okay, so you can see in this video that it try to go as deep as possible along this route, and at this point it have two possible paths, so it chose to go up, and when it explore all the routes as the upper choice, after exploring all the choices as the upper choice, it will do a retrack and then it will try the lower route. Okay, so and even it start exploring the lower path, okay, it will actually go along one route, okay? It will actually go along one route until that route doesn't lead to the goal state. Okay? 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 So you can see, from this maze video, you can first of all understand several facts, okay? First of all, the tree search algorithm is a exhaustive search algorithm. Okay, it is a kind of an exhaustive search algorithm. It actually doesn't care about whether the route can get to the goal state. It keep on generating the path, okay, until a path reaches the goal state that it will stop. Okay, it doesn't select the node intelligently. Okay. 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 It doesn't select the route intelligently. Okay. And let's consider this. Okay. If the algorithm already be sure about which node can get to the goal state, then there is no point to do the search in the first place, right? Okay. So the algorithm doesn't know which route can get to the goal state. Okay. So as a result, the search must be performed in kind of an exhaustive manner because you don't know which route can get to the goal state. So you need to try out all of that. Okay. So if you refer back to the lecture notes, if you use our example in the lecture notes, okay, in the search tree you see in this slides, okay, we have the factors, the ODS, the remission region, the series and TV solo, okay. We have these 5 states and we have one path that get back to the initial state, okay. So ignore the looping, okay, that go from the initial state back to initial state. We still have 1, 2, 3, 4, 5. We still have 5 nodes that we don't know whether it can get to the goal state. So the best solution is that I just try out all of them. And just try exploring all of them to see if I can generate more path from these 5 states to get to the goal state. Okay? As long as one of them can get to the goal state, then my mission is accomplished. Okay? So you may think that this idea is not intelligent, but this is essentially how the algorithm search the pathways. Okay? You need to understand one concept. Okay? If the algorithm already know which node we sure have a path get to the goal state, then we don't need to solve the problem in the first place. Okay? Our algorithm is aimed at finding a path that reaches the goal state. If I can have a function that I can determine which a node can reach the goal state or not, then I don't even need to run the search algorithm in the first place. Okay, makes sense, right? Makes sense, right? So that is the reason why we will need to explore all the nodes all the unexplored nodes in the search tree in an exhaustive manner. Because you just don't know, you just have no way to know whether which path can get to the goal state. Okay? Okay. But the foundation issue is what node to be picked for exploration. Okay? And from this example, you can actually see that if the strategy of choosing what node for exploration is different, then the search algorithm behavior will be vastly different. Okay? And these are the things we would like to discuss in the following lectures. Okay? So any questions? Any questions? Okay? So the next question is, so we know that the breadth search is prioritizing the shadow nodes. And we know that the depth search is prioritizing deeper nodes. Then the next question is how we implement the search strategy. Okay? How we implement the search strategy, okay? And essentially that will be the main focus of our discussion. How we implement the search strategy, how we create an item, how we create a thing that can intelligently select the deeper node for shadow node for exploration. And that is the thing we need to discuss. Okay? And before we talk about the strategy, we will talk about how we evaluate the search strategy performance. Okay. When we are talking about the strategy, okay, we can talk about the completeness, the time complexity, the space complexity, and the orthogonality. Okay. So completeness means that given a problem as a solution, can your search algorithm always able to pick it up? Okay? Okay. And the second one is times complexity. Essentially, we are talking about how much time our algorithm needs to take to finish execution. Okay? To find a solution. Okay? And I believe that you should have learned the concept of complexity in data structure for data science student, right? You at least know what is complexity, right? Okay. And for students who have not studied data structure, you can consider the concept of complexity in this manner. Okay, so the idea of comparing algorithm is a little bit tricky. Okay, the most intuitive way is that I have an algorithm and I just execute the algorithm on the machine or based on some data set, okay, and comparing the runtime that I know what algorithm performs the best. Okay, but sometimes the algorithm sometimes the algorithm will take a long time to finish execution. Then if we need to really do experiment to determine the execution time, it needs to finish a task, then it may be wasting a lot of time. Okay, if we can do some analysis and we can determine the algorithm will take a lot of time to finish a task, then we may not try out in the first place. We may try to develop an even better algorithm in the first place. Okay, so sometimes we want to use mathematical or analytical skills to determine how long a algorithm need to execute. Okay, and essentially, the idea is that when we try to do things in an analytical manner, then we cannot assumption like what algorithm will be executed on what computer. Okay, so if I am analyzing the performance of a algorithm in a general analytical manner, then I would not be measuring the algorithm performance on a single computer. I would like to have a measurement that is universal. Okay, that is not dependent on what computers I'm using. Okay.
Can you give me an example?
Let me get to the details when I'm finishing laying out the foundation. Okay, so let's consider this. Okay, I want to compare two algorithms. If I execute them on two computers and I get two runtimes, okay, because they are executed in two different computers, then comparing their runtime will not be fair. Okay, I run the algorithm on a state of the art server. Okay, and another algorithm I run it on a simple computer that you can find in a second-hand store. Okay, then the execution time of these two algorithms is not comparable because the background computer you are using are different. Okay, so we want to have a measurement that is not dependent on the computer, that we can derive it based on the analytical analysis on the algorithm alone to give us a brief idea on how good the algorithm is, how much time it takes to finish a task. Okay, then what we come up is complexity. Okay, complexity is essentially measuring how much time you have the upper bar of your algorithm needed to finish a given amount of tasks. Okay, for example, I have n amount of data. Okay, I have n number of data. Okay, then I will measure how much time my algorithm need to finish those n number of input as a equation in the terms of n. Okay, so for example, this algorithm need to take n square, okay, n square operation to finish n data. Okay, then that will be called complexity. Okay, and to make us able to compare it easier, okay, we'll take the upper bar. Essentially, if, for example, if a algorithm needs to have n square plus n plus 1 operation to finish a task, they will just take the highest power term and we will say the algorithm needs to have n squared number of operations to finish that task, such that we can compare the algorithm in a more straightforward approach. Okay? Okay, and we are essentially establishing an upper bound for our algorithm. Okay, so when we say the algorithm needs to take a O(n) square complexity to finish n data point, it means that at most the algorithm need to take n square operation to finish a n task. Okay, you may ask this, Professor, so why a operation in n square plus n plus 1 operation I can represent is n square? The reason is that we assume the n can become very large.
Yeah, and the one is not very significant.
Yeah.
We can.
Yeah, so if the n is extremely large, then the n squared will be vastly bigger than n and 1. Okay, so we can ignore them all together. So that is the reason why when we are measuring the performance of the algorithm based on the number of operations we need to do, we are taking the highest power item. Okay, in the equation, in the number of operations equation. Okay. So also, up to now, I have given a very brief explanation on complexity. Okay, okay. And for the students who have learned data structure, you must have learned it. Okay, you should have learned it, right? Okay. Or you learn it, but you don't recall it right now. Okay. So the take-home message is that complexity is measuring how much operation your algorithm need to execute on n number of tasks or n number of data points. Okay, and we are measuring the instruction it need to do in terms of n number of data points. Okay, so an algorithm may take n square or n number of operations to finish n data points. Okay, by using this terminology, then I can compare the performance of two algorithms even without a dedicated computer to do experiment. Okay, I can just say that this algorithm takes n square to finish a task, and this algorithm needs to take n number of n to finish n tasks. So the second algorithm will be better. Okay, okay. So any questions? So any questions? So any questions on the time complexity? Any questions? Any questions? Okay, any questions? Any questions? Any questions on the concept of time complexity? Essentially, in time complexity, we are measuring how much instructions your computer need to take to finish an algorithm. Simple as that. Okay, but we do the measuring in terms of the n number of data points that is different times. Okay, we assume that the algorithm will take n data points. Okay, so we can express the number of operations that the algorithm need to operate in terms of n. Okay. Okay, so any questions? So any questions? And the second one is called space complexity. Space complexity is referring to how much item that you need to store in the computer memory to finish the execution of an algorithm. Okay? You may ask this, Professor, so I understand that I want to know time complexity because I want my algorithm to be executed rather quickly. Okay, I want it to get my results as soon as possible. But you may ask is why space complexity is essential as well. So the idea of space complexity is to measure how much memory your computer needs to take to execute a task. Okay. Most of you here, I believe that you must be using smartphone a lot. Okay. So I believe that you may have the experience that I am now playing a mobile game, okay? And when I finish playing the game and I exit the game, then suddenly all the apps I previously opened have already been quitted. Okay, okay. So you may have this experience, okay? Especially you are using a phone especially you are playing a 3A standard mobile game, okay, like Genshin Impact, okay? Or uh, or like I don't remember the English names of those mobile games. I know the Chinese name, but I don't recall the English. I only know 原神 is Genshin Impact, okay? So you assume some free games like Genshin Impact, okay? You are running them on your phone, okay? And after you play the Genshin Impact and then you quit the game and then you try to launch another application and then you try to return back to other application, okay? You may discover that the application you previously opened is now already quitted by the mobile phone, and your mobile phone need to start the application from scratch, right? Have you ever had this experience? Do you have this experience? I originally opened up WhatsApp or Facebook or WeChat, okay, and I'm discussing with my friends. And after I discuss with my friends and I play Genshin Impact and I quit the game and then I suddenly found that all the apps I previously opened are now closed and I need to restart that. Okay? The reason why is that the game take up so much memory that the mobile phone need to kill other apps, need to stop other apps to allocate enough memory for the game. Okay? Okay? So how much memory being used in your computer program can actually affect your user experience. Okay? Okay? Does that make sense to you now? Does that make sense to you now? Okay? So we don't just want to take a look on time complexity. We also want to take a look on space complexity because we don't want our app to take up so much memory. Okay? Okay? I don't know if you have this experience, okay? If you have a very old phone, okay? The old phone may not be even to start a 3A standard mobile game. Simply because it doesn't have enough memory. Okay? Or it will become very slow because it doesn't get enough memory. Okay? Or if you have or you may heard the older generation say that whenever your computer is slow, buy more RAM. Okay? So all these are actually related to the fact that your algorithm, your program need to take up memory spaces in the RAM to execute. Okay? And as a result, if your algorithm or program takes up more RAM, then this is not a good thing. If your program needs to take up more RAM to execute, then your computer will not have enough RAM to execute other applications, such as you cannot when you execute Genshin Impact, okay, all the other mobile applications like Facebook, WhatsApp, are all killed because the phone doesn't have enough memory, okay? So this is not a good thing to have, okay? So as a result, we want to not take a look on the space complexity as well. Okay? Okay? It makes sense now, right? Right? So for the space complexity, we'll essentially measure how much data point that we'll need to store in our main memory, okay, for our algorithm to execute. Okay? And we are measuring the number of nodes that we need to store in the memory, and we are measuring how much data point we need to store in the main memory, because by doing so, we can avoid sticking our measurement to a single computer and allow us to compare the algorithm more efficiently. Okay? Okay? So any questions? Any questions? Any questions? Any questions? Okay? So that is called space complexity. Okay? And you may actually find that when we are using the number of instructions or number of data points that we need to take to run the algorithm, we are in fact measuring the performance of our algorithm in an abstracted approach. In an abstract approach, we abstract away the technical detail on what CPU or what GPU or what memory that you have in your computer, or how many or how many bits or whether your computer is executed on 32-bit or 62-bit. We are abstracting all the technical detail such that we can compare the performance of our algorithm in a sense that we don't need to run experiment to compare them. Okay? Okay, that is the reason why we use complexity as the measurement. Okay, the moment we use complexity, we don't need to run experiment to test the performance of our algorithm. We can do it analytically. Okay, okay. So any questions? So any questions? So any questions? So I believe that most of you have the mind that if I want to know the performance of the algorithm, I can just run it. So why I don't do it? And the reason why is that if we use complexity abstraction, then I can have a symbolic, a theoretical upper bound for my algorithm, and this upper bound is measured in a standardized, in a completely standardized terminology that when I'm comparing the performance of two algorithms, I just compare it just like comparing numbers. Okay? Okay? If I tell you one algorithm take 10 minutes, and our algorithm takes 5 minutes to execute. Without knowing what computer that two algorithm is executed on, I don't know how to compare that. Okay? Maybe one algorithm is executed in a state-of-the-art GPU, and the other algorithm is executed on a second-hand computer you can get in a thrift store. So how can I compare these two algorithms in an objective manner by taking a look on the runtime only? But introducing the complexity, I abstracted all these technical details, and when I'm comparing O(n) squared versus O(n), I know that O(n) will run faster. Okay? And that's the reason why you learn complexity. Okay? Okay? So the final one is called optimality. Okay? So we want to see if our algorithm can always find the optimal solution. Okay? That in our sense, that is, if our solution have the least cost. Okay? So any questions? So any questions? So any questions? You just need to remember time complexity is measuring the instruction that need to be taken, and space complexity is measuring how much data point the algorithm need to put in the main memory, and that will be okay. So that is as simple as this. Time complexity equal to number of instructions. Space complexity equals to how much data point is stored in the main memory. Okay, you just remember it. Okay, you just remember it. Okay, and we assume that all the algorithm takes n inputs. Okay, okay. Then measuring the time complexity and the space complexity will be in the number of data point, will be in terms of the number of data point that is in n in the term of n. Okay, okay. Then that will be good enough. Okay, then that will be good enough. Okay. And essentially, we can have two different types of search algorithm. One is called uninformed search, and the second one is called informed search. Okay. For the uninformed search, essentially you just have the problem definition. Essentially, you just have the space diagram. You just have the search space diagram. Okay, but you don't have an indicator. You don't have any extra information telling you what route will actually get you faster to the goal state. Okay, so you need to exhaustively check all of that. But for informed search, we introduce some heuristics. We introduce some function that mimics human intuition. Okay, that mimics human intuition to do the exploration. Okay. Okay. So if you take a look on the if you take a look on the wait. If you take a look back on the maze example, okay? So you can see the why the search algorithm like the breadth first search and the depth first search they would not go optimally, okay? Is because for the breadth search, it only knows what is the possible pathway along the edge here, okay? Along the edge, okay? It doesn't know which point can get to the goal state. So it have no choice but to do all the exploration, okay? To do all the exploration. And for the depth search, it only knows the nodes at the edge. It doesn't know which edge can get to the goal state. So it will just select one of them and then explore it as much as possible. And if that route doesn't get to a goal state, then it will try to select other point and to do exploration. Okay? So that is what we are talking about. The agent knows the problem definition. The agent knows whether given a point, the point can get to what neighbor. Okay? But whether a node can get to a goal state is not something that is available in the problem definition. Okay? The problem definition that always tells you that at what state the agent can travel to what other states. Okay? Given a state, through the problem definition, you can always get all the neighboring states. Okay? So the visibility of the agent is severely limited. Okay? Okay. So for the buffer search, it only knows the node at the edge. Okay, it only knows the node at the edge. And for the depth search, it also only knows the node at the edge. So that is the reason why it needs to do it exhaustively. Okay, because it doesn't have any hints telling the algorithm what route is the best. Okay. Okay. And in the lecture 4 notes, okay, in the lecture notes 4, okay, we will actually talk about informed search. For informed search, we will actually create a approximation to compute how likely a route can get to the goal state. Okay, okay. Or I would say is the cost of a route going to a goal state. Okay, we can estimate that. Okay, by estimating that, we can actually prioritize nodes that is more likely to get to the goal state faster. Okay, so informed search can allow the search algorithm can kind of intelligently get to the goal state. Okay, but that is a catch. Okay, the approximation is not always accurate. Okay, the issue is that if there is an algorithm that tells you that, if there is a function that can tell you that that node can get to the goal state with no cost at all, then I don't need to run the search algorithm in the first place. Okay, if I have a function that can tell me that a node can go to the search space in an instant, then I don't need to run the search algorithm in the first place. Okay, makes sense, right? Makes sense, right? So that is the reason why we, even for informed search, we will do it with a heuristics or a approximation. Okay? Okay. Whenever in data science and computer science, whenever someone use the term heuristics, it always means approximation. It always means iteration. Okay? So when you heard a term called heuristic algorithm, that means that the algorithm must have certain approximation or randomness built inside of it. Okay? If the term heuristic means that the algorithm cannot give you an exact solution. Okay? Okay? I understand that most of you here are used to learning algorithm that give you an exact solution. But in fact, there are many algorithms that can give you an approximation of a solution, approximated solution. And that is done by purpose. In some situation, given an exact the best solution will take a very, very long time. But an approximated good solution will take you far less time. So as a trade-off, will be settled up with a not ideal but approximately good enough solution. Okay? Okay? Okay. So any questions? So when you heard the term heuristic again, you must know that that algorithm must have some randomness or maybe an approximation or maybe not quite correct, not quite accurate in some situations. Okay, so that is the terminology heuristic meaning is. Okay. Okay. So the backward search, okay, essentially backward search is to try to do the search in a layer by layer fashion. As you can see in the slides, that the backward search starts searching from the root node of the search and expand all successor or at the current level before moving to the node of the next level. Okay, so that is the reason, that is the exact reason why if you take the video of the maze, the backward search on the left-hand side, it is doing the search in a wave style, like a wave from the left-hand side to the right-hand side. And that is the reason why, because it is doing exploration in a layer by layer, level by level, or one depth by one depth fashion. Okay, okay, okay. So essentially, it prioritize shadow nodes. Okay, it prioritize shadow nodes. Okay, and you may ask is, Professor, how it prioritize shadow nodes? Essentially, it prioritize shadow nodes by using a queue as the fringe. Okay, let's recall the general tree search algorithm. In the general tree search algorithm, you learn that we have a thing called a fringe. The fringe is essentially a data structure that keep track on the nodes that have not been explored, and it also responsible to return a node for you for exploration. Okay, okay. So if okay. So if we program the fringe, to select the shadow node from the search tree, okay? Select the shadow node from the search tree, then our general tree search algorithm can then be programmed as the backward search. Okay? Okay. The key of the implementation of the backward search is that we now have the fringe in the general tree search algorithm. Then the fringe is responsible to return a node for you for exploration. Okay? Okay. So now the issue is that whether the fringe can return the shadow node in the search tree for you. Okay? So let's recall our example in the search tree. Okay, so let's imagine this. Okay, so now the fringe, okay, should be recording Fragorus, OTS, Mitchell Richard, series, and Timmy Solar. Okay, so our fringe must prioritize and return the series and the Timmy Solar right before the Fragorus, the OTS, and Mitchell Richard. Okay, it makes sense, right? Okay, so if our fringe is able to prioritize series and TV Solar over the Fragorus, ODS, and Mitchell Richard, then our fringe is able to perform the backward search. Then we can make our fringe able to make the tree search algorithm can do the search in a backward search manner. Okay, okay, it makes sense, right? Up to now, it makes the fringe clicks in, right? Okay. So now our issue is how to prioritize series and Timmy Solar with a data structure. Okay. The fringe is just a data structure. We don't have a lot of coding that we can work with. So how we can use a data structure to prioritize series and Timmy Solar in this search algorithm, in this search tree. Okay. And let us make an observation. Okay. We generate the search tree from the top to the bottom in a layer by layer approach. Okay? Okay? You have this observation, right? So as you can see here, we start off from the initial state, okay? And then next we add one layer of the nodes, and then we do exploration, and then we add one more layer of the node, okay? So the node of the search tree is added to the search tree from the top to the bottom approach, okay? It is added at the bottom side, okay? Okay. So shadow node having a lower depth value, it means that that node is added to the search tree earlier. Okay? Okay, it makes sense, right? It makes sense, right? Because the search tree is generated from the top to the bottom in a layer by layer fashion. Okay? That means that the node at the shadow node, okay? The node with a smaller depth value means that it is added to the search tree earlier. Right? Right? Okay. You may take a look back in the animation, okay? So you can see here the series and the Temisora are added at this point, and after the series and the Temisora are added to a search tree, we now add the factors, the OTS and Remedial region into the search tree. Okay, so clearly the search tree the shadow node means that it is added to the search tree earlier. Okay, okay, okay. Okay. And the deeper nodes are added to the search tree later. Okay? It makes sense, right? It makes sense, right? So prioritizing shadow nodes over deeper nodes now become a problem of selecting earlier nodes over later nodes. Okay? Okay? Selecting shadow node over deeper node now become a problem of selecting earlier nodes than later nodes. Okay, the priority of the node depth now becomes the priority of the ordering of presence. Okay, originally we want to prioritize node that is the shadow node over deeper nodes. We want to do the prioritization based on the node depth. Okay, but now if we take into consideration that shadow node means the node appears earlier and deeper nodes mean the node appears later, then the problem of prioritizing the depth of the node now becomes prioritizing node that appears earlier. Okay? Okay? Up to this point, any questions? Up to this point, any questions? Up to this point, any questions? Any questions? Is the frame still clicking now? So now let's recall what you learned in data structure. Have you learned the data structure that the thing that is added earlier will get processed earlier? Have you learned the data structure like this? Have you learned the data structure in have you learned the data structure that the things that is added earlier to that data structure will get processed, will get extracted earlier? You learned such a data structure, right? Yes, a queue. Okay, so that is why in the breadth search, we essentially just replace the fringe as the queue. End of story. Okay, okay. So that is why it seems the idea of search strategy is just such technical fancy words that you can heard in some sci-fi movie, okay? But essentially, it is just using the queue as the fringe.
Nothing special.
Okay, it's nothing special, okay? But the whole idea of why a queue is good to be the fringe will involve the discussion that I've just done. Okay, we just don't choose the fringe out of nowhere. Okay, I can actually deduce with your full reason why we want to use the queue as the fringe. Okay, And that is also the reason why you want to study data structure. Our university will actually arrange you to study data structure in the first place. Okay? The data structure will actually affect your algorithm design. Okay? If we do not have the idea of the queue, then we will need to come up with a very complicated algorithm to implement the search strategy. Okay, we may need to have an index for the node, and then we need to do some sorting or whatever. Okay, but with the queue, we just replace the fringe with the queue. Then end of story. That is vector search. Okay, simple as that. Okay. Okay. So maybe I will do some revisioning. Okay. In case you don't know what is queue. Okay. Also you can get the information from the extra logs. Okay. So essentially a queue is a data structure that there is a head and there is a tail. Okay. And when you add items, you add it to the tail, and when you extract items, you get it from the head. Okay. So it essentially is the same as you are trying to buy concert ticket. Okay, I believe that not the current generation will still go physically to buy concert ticket, right? Okay, so when you are buying concert ticket or when you are buying lunch at the canteen, okay, then you will need to line up your line in before the kiosk, okay, or before the selling point, okay, before the register, okay. Then the one that get to the kiosk first will buy the food first. Okay, so this is essentially how queue is actually performed. Okay, and because this is not a data structure course, so we will be using the DQ, okay, the DQ library to facilitate the emulation of a queue. Okay, the DQ in the Python is essentially a double linked list. Okay, so you can use it to emulate a queue or as a stack. Okay, so we can totally use DQ to emulate a queue. Okay, you can try to execute this code at home. Okay, so the append is adding item to the right hand side, and the port left is getting data out from the left hand side. So by having left hand side as the head and the right side as the tail, then if you keep on having this logic in your coding, then the DQ can become your queue. Okay. Okay. So it's as simple as this.
So technically, the head can be on the right, right?
Yeah. You just change the code, and then that will be it. Okay. But we just use the left and the head and the right as a tail, then call it day. Okay. Okay. We just do it for the sake of simplicity. Okay. We just do it for the sake of simplicity because this is not an algorithm, because this is an algorithm course, but not a data structure course. So I do not I'm not trying to be fancy about the data structure. Okay, as long as it can function as a queue, then that will be great. Okay. Okay, you already learned how to implement a queue or a stack in the data structure course. I don't want to repeat those facts. Okay. Okay, you learned already. Okay. Okay, so I don't want to repeat. I just call command library and do the job. Okay. So any question about the queue? Any questions? Any questions? So essentially, okay, we go through this example, and then we can end today's lecture. Okay. So at the left hand side region, okay, this will be the region for our search tree. Okay. And at the right hand side, here will be our state space. Okay. For the sake of simplicity, okay, I am using a simplified map. Okay, otherwise the search tree will be very large. Okay, the search tree will be very large. Okay, so I use a simplified search space, okay? And at the right bottom corner here, at the right hand side bottom corner here, this is the fringe or this is the queue, okay? So we start off as stable. So the stable is our initial state. So we put the stable as the queue, okay? And now the stable is the item, is the data structure, is the element in the queue, okay? So it get removed and we try to do exploration on it, okay? In the state space diagram, you see the stable is can go to Mitchell Richer and to go to Fredgorus, okay? Okay. Okay, the arrow is pointing the direction of actions. Okay, so there is an arrow from Cebu to Fredgorus. So there you can go from Cebu to Fredgorus. Okay, but because the arrow is not pointing from Fredgorus to Cebu, so you cannot go from Fredgorus to Cebu. Okay, the arrow is telling you the direction of the actions. Okay, I'm imposing this is to simplify the state space as well. Okay, otherwise the state space will grow, the search tree will get very big. Okay. And in some situations, you may actually see state space with arrows. So I am adding arrows here for demonstration. Okay. So when you explore Cebu, the Cebu is removed from the queue, and the Cebu, according to state space, is control Fredgorus and Remedial Recharge. So Remedial Recharge and Fredgorus is added to the queue. Okay. Okay. And then we explore, and then because we have the Fredgorus here, so we extract the Fredgorus, and the Fredgorus can go to Bucharest, okay? So we add Bucharest to the queue, okay? But now we have an issue, okay? We now have an issue. Bucharest and Remedial Recharge are both unexplored. So we should re-explore first. And as you can see here, because this is a queue, and queue will prioritize earlier node first, so the Remedial Recharge will get explored first. Okay? So the Remedial Recharge will get explored first. Okay? And when we explore Remedial Recharge, from the diagram, we can see that Remedial Recharge can go to Pithesti and go to Canberra. So we add these two into the search space and we add to the queue as well. Okay? Okay. And at the end, okay, then we will explore the Bucharest, because the Bucharest is the first node in the queue, so we explore Bucharest. And because Bucharest is already in the goal state, then we can stop right here. Okay. So as you can see here, this is the breadth search algorithm execution. Okay? Okay. You can see that the choices of the Bucharest and Remedial Recharge is done, the selection priority is done by the nature of the queue. The queue will prioritize shadow node first, the queue will prioritize earlier node first, so the shadow node will get prioritized first, and that is the reason why Remedial Recharge will get expanded rather than Bucharest. Okay, although you may think that Bucharest should get explored right now, but because the queue is implemented in the sense that it's explored, it prioritize shadow node first, so the Remedial Recharge will get explored first. Okay? Okay? So any questions? So if there is no question, then that will be a good time for us to stop today's lecture. And this is the end for today's lecture, and I will end the recording now. And for the students who haven't